Okay, so we're going to start. So Sarah Rovner-Frydman has been working on separation logic using techniques of category theory, in particular proset theory, the theory of preordered sets. And she's been doing a project about it at Marlborough College, and she'd like to tell us about it. She's very visible at the category theory community server. If you're not looking at this Zoom group chat and you have no idea what the category theory community server is, take a look by going to the little thing on your screen that says chat, and there are instructions for how you can get there. And that's where we're going to talk about stuff after her talk. Okay, so Sarah, go ahead.
Okay. So basically, the general concept of what this talk is about is that there are some techniques that are used. So separation logic is a system or family of systems for reasoning about the behavior of imperative programs that manipulate shared resources. And there are a number of techniques in the literature which you can kind of unify and explain using the pre-existing notion of optics. And you can apply a bunch of category theoretic constructions to kind of come up with new useful, or at least hopefully useful, results similar to those. So first I'm going to go over some background on separation logic, and most of that stuff is fairly standard if you're someone who works in program verification, but given that this is not an audience of people who work in program verification, or at least not primarily, I figure it's probably stuff that's worth going over. After that, I'm going to show what optics look like in general when they're specialized to prosets, which just means preordered set. Proset is to preorder as poset is to partial order. And having done that, I'm going to show how that applies to separation logic. So when you actually specialize that even further to the prosets that are involved in separation logic, how the aforementioned techniques that exist in literature pop out of that. So separation logic builds on Hoare logic, and Hoare logic deals with these things called Hoare triples. And a Hoare triple has three parts. The thing in the middle is called a command, and it doesn't need to be literally a single command or statement or whatever. It's just supposed to be some executable thing, something that can have an effect in the programming language that you're trying to reason about. So it could be a whole program or some kind of scrap of code. The things before and afterward in the braces are called the precondition and the postcondition, and they're supposed to be assertions. So you can formalize this in a number of ways, and it depends on whether you want to approach Hoare logic as, say, a purely syntactic deductive system, or if you're mostly interested in looking at semantic, like taking a semantic approach where you're reasoning entirely in the semantic model. I'm going to think about this mostly the latter way here. I'm going to look at this from a more semantic viewpoint. But either way, the important thing is that an assertion is basically literally an assertion. It's something that can be true at a given point in time while a program is running. It's a claim that you can make about the state of a program, which can become falsified or become true based on how the program modifies the state, or how the code modifies the state. So in these examples down here, and whenever I write assertions, I'm going to use this very common and extremely standard abusive notation, or it's not even really an abusive notation in many formal approaches, but this abusive notation where I kind of don't really distinguish between mathematical variables and program variables when I write an assertion. The meaning of a Hoare triple is if this assertion holds, and then this command runs. If it should terminate, then this post condition will hold. So the overall meaning is something along the lines of like, C has the effect of changing things from P being true to Q being true. You can make this completely formal by saying something like, this is a set of states, this is a set of states, this defines a relation between states, and the image of this lands in this, or something like that, but you don't need to think of it that formally because this is not a talk about Hoare logic. So there's some examples down here. Like, if you know that the value of the variable x is less than the value of the variable y, and these are variables as in like things in your imperative programming language that can be altered by statements, not as in mathematical variables. This is the equivocation I was talking about, the abusive notation. If you know that x is less than y, and they're both integers, then if you assign x to be one more than it used to be, you'll now know that x is less than or equal to y, because that's, hopefully that's intuitive. Or if you have a language where lists are mutable objects, like say in Python, or if you're using something like a linked list in C, then you have a notion of sorting something in place. So maybe if you have the precondition that L is a list, then you can call the function sort in place with it, and that will modify it so that the same list is now rearranged. And then in the post condition, you can assert, just using ordinary mathematical language, you don't need to write an algorithm or anything, that it's in order. And this last one is a little bit subtle, but it illustrates the difference between Hoare logics of total correctness versus Hoare logics of partial correctness. In a Hoare logic of partial correctness, things work the way I described, where if the precondition is true, and then you run the command, if it terminates, the post condition has to be true. In a Hoare logic of total correctness, what the meaning of a Hoare triple is if the precondition is true, the command, and you run the command, it has to terminate, and then the post condition will be true. So this Hoare triple is true if you're working with partial correctness, because this will never terminate if this precondition is true. So this post condition will always be true if it terminates. But in a Hoare logic of total correctness, this Hoare triple is false because, well, this won't terminate. Somebody has their mic on. Is there a question or anything?
It's Kaushik.
Kaushik? I don't know what's going on. So here are some example rules that are valid in Hoare logic. This kind of notation is pretty common in like logic and programming languages work. I don't know how common it is. I don't think it's that common outside. It just means that if all of these are true, then you can conclude this, and any variables that are not explicitly quantified are just universally quantified. So this entailment relation means that P prime entails P means that if P, in any program state where P prime is true, P must follow. So it's roughly implication. There are some subtle differences. It's more of a meta level operation, whereas implication combines assertions. But don't worry too hard about it if you don't have background in logic and that isn't clear to you. So this is the rule of consequence, and it says basically that if you have a Hoare triple, then you can weaken it by altering the precondition and postcondition on purely logical grounds. So there are rules for reasoning in Hoare logic based on what stuff in your programming language does. This is what lets you reason based just on logical relationships of statements to each other. So if you know that Q will always be true after C runs, and then Q entails Q prime, you can know that Q prime will always be true afterward, and in the other direction, you can do the converse. And then similarly, you have a bunch of rules that allow you to build up Hoare triples for saying things about programs that are built out of various kinds of constructs. And I'm not going to be using this kind of rule. I'm just showing it as an example. So the frame problem is, if you want to reason compositionally in a system like Hoare logic, you need to be able to take a known true Hoare triple and then combine it with other Hoare triples about code that manipulates unrelated resources. So if you have some piece of code, it's only going to be dealing with part of the system that it's a piece of, and it's only going to manipulate some of the resources that the overall system deals with. And if you're going to state what the code does, you should only need to talk about those resources in the Hoare triple. And then if you have two different pieces of code, then you have two different Hoare triples, and they both talk about different resources. And then if you combine those pieces of code into a bigger piece of code, and you want to write down a Hoare triple for the bigger piece of code, if you want to reason compositionally, hopefully you should be able to combine the smaller Hoare triples that you've already proved into a bigger one, using some kind of reasoning or rule that allows you to say, okay, this piece of code only works with this piece as part of the state, this piece of code only works with that part of the state, let's put them together, and we can just hold on to our knowledge that was already true from about that, and sorry, that's maybe a little unclear, but essentially you might want something like this to work. You might want to be able to say, if whenever you run C starting from P, it makes Q true, then if you have some other facts that deal with other parts of your system, then you can just hold on to those. And this works for some kinds of things, like maybe you have this Hoare triple for just this one thing, and this is in the middle of some other code that deals with some list, and this doesn't touch that list at all. So, and you need to be able to hold on to that information that the list is sorted. So you want to be able to conclude this, and that would be a typical kind of application of a rule like this, hypothetically. But this rule is not sound, and maybe it's even obvious why to some people. Let's say that you have a notion of some kind of object representing a button which is pressable, and a button remembers if it's been pressed, but also all buttons globally share a counter of how many times all buttons have been pressed. So that's this shared information. And if you have a Hoare triple like this, which says that if you have a pressable button and you press it afterward, it will have been pressed. You can't just take this knowledge that things have been pressed, there have been 3 total presses, and hold on to it afterward, because it's no longer true. The basic problem is that in this case, F is invalidated by C. You can't just hold on to arbitrary Fs, because if C modifies the underlying resources that F relies on in order to be true, then F won't be true afterward. So this kind of naive frame rule doesn't really make sense, because you can only really hold on to information that you have some way of knowing won't be altered by the fragment of program that you're dealing with. And that's kind of a subtle issue in general. And separation logic is a solution to a large class of similar or easy to deal with cases of this, or even some difficult to deal with ones. So what you do is you introduce these new connectives called separating conjunction and separating implication, or magic wand. First of all, you need to have a way of talking about fragments of program states that only contain some portion of the overall resources and data. And then you need to give away a notion of how a program state or fragment thereof can break down into disjoint smaller fragments that split its resources and data between them. And second, you need to generalize assertions from things that can hold in a given state to things that can hold in a given state fragment. And then these are the rules that hold for your new connectives. These are the ones that hold for the traditional versions of conjunction and implication. So for ordinary conjunction, so for ordinary conjunction, something is true in a given state fragment, a conjunction is true in a given state fragment just if both of the conjuncts are true. But for separating conjunction, P star Q is true in a given state fragment or state if P is true in part of it and Q is true in another part of it, and they're disjoint parts that add up to the whole thing. So this means this is supposed to capture the idea that P and Q are true for like separate reasons that don't overlap, so that you can modify the underlying data that is the reason for P being true without having any effect on whether Q is true. Similarly, and separating implication or magic wand is a similar kind of thing, but the real reason for defining it, arguably, is that it's the thing which is adjoint to separating conjunction, similarly to how implication is adjoint to conjunction. Separating implication is characterized by this property. This is like a hypothetical derivation. The idea is that if, I need to clarify the quantification here. These are sort of existentially quantified. The idea is that if there are some pieces that you can break this down into, then this holds. So you just need to be able to split this up into two pieces. It doesn't matter which ones they are. Whereas this needs to hold for any choice of this that can be put together with this to make something that satisfies Q. So the idea is that this satisfies P1Q if for anything that satisfies P, which you can add to it, the overall thing satisfies Q. So like, it's sort of like saying P implies Q, except that the P needs to hold in the new thing being added. It's a little tricky, and it kind of has a reputation for being less intuitive than separating conjunction, but it's sort of like a version of implication where the premise needs to come in from a separate area. It's like you're introducing a new resource when you're introducing the premise.
So David Spivak had a question, which is, if black circle implies Q, I'm reading this.
Models, is that relation?
Models, okay. If the big black circle models P, for example, does that imply that a half black circle models P?
Probably not, no. For example,
I guess
if P is something like you have list 1, 2, 3 in memory, then the kind of breaking stuff down that we're talking about would be something like maybe you split memory into a couple of pieces, like one contains the first item in the list, one contains the second item in the list, one contains the third item in the list. So none of those would satisfy containing the list 1, 2, 3. Mm-hmm. However, if you want to ask about whether if half black circle models P, then will full black circle model P, that makes the difference between affine separation logic and linear separation logic. And so yes, there are some separation logics where you can say that factorization of states, where satisfaction is always monotone in factorization of states, but not every separation logic satisfies that, and there are good reasons why you might want it or you might not want it. But this is not supposed to be a talk where I go into a ton of detail about separation logic, even though it kind of has become one.
Okay, thanks. Yeah, you're about 1/3 done with your talk.
Oh, geez. Okay. Anyway, if we state the frame rule using separating conjunction instead of ordinary conjunction, it is sound. Modulus and technical details about variable occurrences. The most classical version of the frame rule has the side condition on whether variables can occur or not. You can reformulate it in ways such that it's valid if you see it like this. Technical details, don't worry about it. The examples like this one, where the naive version with ordinary conjunction worked, these still work for exactly the same reasons. In cases where it would have broken, it gets ruled out by the separateness condition. And so like for this one, this Hoare triple is now true because the premise is vacuous, or sorry, the precondition is vacuous. It's true that if you have a state where there are 3 overall presses and you have a pressable object and you have a pressable object, blah, 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 then that won't work. But this is never going to be separately true, because in order to say that this is pressable, this object needs to have access to the global counter. And in order to say that there have been 3 overall presses, you need to make a statement about the global counter. So these both need to talk about this global counter, and therefore they can't separately hold in different disjoint fragments of the overall state. So this statement is never true in any state fragment. And so this triple is just vacuously true. And so the frame rule basically works. By using separating conjunction, you sort of, you make the frame rule work by making this conclusion no longer usable in cases where these overlap, which rules out the cases that otherwise would have broken. And that does mean that there are certain kinds of statements like this that seemed useful that are now vacuous, and it seems like maybe it would be hard to talk about them, but there are usually ways of reformulating it. But again, that would take a while to talk about. So separating conjunction is still commutative and associative. This is just double entailment. So this means like logical equivalence of assertions. So this hinges on composition of resources being commutative and the underlying thing. Like you could reformulate this at the formal level, like the formal definitions involved in separation logic. Sorry, that's a tangent, never mind. This is commutative, this is associative, but it's not idempotent like ordinary conjunction. So if you have an ordinary mathematical fact like 2 squared equals 4, then you can say that 2 squared equals 4 entails 2 squared equals 4 and separately 2 squared equals 4. But you can't say, for example, let's say that you want to say the third item in this list, L, is 5. That doesn't entail third item in the list is 5, star third item in the list is 5. And that's because these won't be true separately. You can't break the state into 2 different fragments such that this is true in one and this is true in one, because only one of them will contain the portion of the list with the third element. So, or at a more intuitive level, these are not separate facts. Like you can't alter the underlying reasons for one of them without altering the underlying reasons for the other. So you can't duplicate this. And even if you existentially quantify this so that you're saying there is a 5 in the list, you still can't duplicate it, because let's say that you have a state where there's exactly 1 5 in the list, then this premise would hold, but this conclusion would not hold, because if you split the state into 2 parts, in one of them, if this would hold, in the one that gets the single 5 in the list, but in the other one, this wouldn't hold because there wouldn't be any 5s in the list in that part one. So you can't duplicate this in the case where the list contains only one 5 in it. So this doesn't hold in general, so you don't have this entailment. So spatial information kind of acts like, so assertions for which identified spells are called spatial, which I believe is because they say something about resources, and traditionally the resource in question is some kind of space in memory, or it's like they take up space. And spatial information acts kind of like a conserved resource. Like each conjunct needs to hold in a disjoint fragment of the state. So it's almost like knowledge of a piece of spatial information is tied to exclusive ownership over the chunk of resources it concerns. So like, if you know something, then you have control over the thing it talks about. And so you can't duplicate it, because that would mean that there's conflicting control. So in order to use modus ponens with wand, you have to give up that ownership. And conversely, if you have knowledge of P1Q, you can kind of see that as carrying the ownership of all the resources involved in Q, except for the ones tied to P. Because if you look again at this illustration, this entails P1, this models P1Q. If adding something that satisfies P gives you something that results in, that satisfies Q. So this carries the underlying resources of Q if you add something that's that satisfies P. So knowing this means knowing something, means carrying exclusive access to Q, to the stuff talked about in Q, except for the stuff talked about in P. So it's almost like a kind of subtraction. So for example, like if you have a pair P, then knowing that the first item is 3 entails that knowing that the second item is 4 wand P equals, okay, I'm sorry, I'm gonna skip forward a little bit because I've used up half of my time and I'm probably not quite halfway through the slideshow. So this is an admissible rule. You can prove this using the frame rule and the various other rules of separation logic and just properties of the connectives. The rule on the slide is more or less the Ramified rule from the citation here. The ramification they mean is this entailment here. And the idea is that this entailment says that if you know R, you can break that into 2 disjoint, independently true facts. P, which is what you really want to know, because that's what the precondition of C is, and some other stuff. And the other stuff gets black boxed as just something that's sufficient to establish this modified R prime if you put back a modified version of PQ back. So the idea is like this global assertion R becomes R prime after a local transformation from P to Q is what this asserts. So the idea is that you can like pull out P from R, and then if you modify it and you replace it with Q, you can put it back in and get R prime. And you can actually reason that out, like I said, using the frame rule and so on, and show that knowing this ramification, and knowing this Hoare triple lets you conclude that the overall effect of this C is this bigger global effect. So this paper is about using this kind of concept to do reasoning where you need to make local transformations in order to affect global transformations in ways that are a little subtle, and you actually have to independently prove that the relationship is what it should be, as opposed to just focusing down on an obvious subpart. So this ramification is an interesting fact. And there are some other results in the literature that use similar kinds of techniques. So this paper, Magic Wand as Frame, does a similar thing where it sort of advocates for encoding certain kinds of partial data structures using wand and like a for all. So you can encode the idea that you have a partial data structure in memory by saying that you have something where you can fill in a hole and get a certain result. And if you ask me, this looks an awful lot like a lens. Like if you've worked with lenses, you can write down their type as something that looks pretty much like this. You put in something, you get out a pair of the thing that you're viewing and something that you can use to put back to get the updated result. And that's exactly what you're doing. Like, this description pretty much matches what you're doing to your knowledge as the program runs. So it turns out that that is in fact true. Like, that's not just an analogy. That's formally true if you use the right definition. And I will explain that now if I have time, because I've used up half my time already. So are there any questions in chat or anything? Should I just go forward?
Just go forward. Yeah, there's nothing terribly urgent.
Okay.
People are just chatting.
So to reiterate, because I guess this is not the most standard term in the world, a proset is just a preordered set. So proset is to preorder as poset is to partial order. Sorry. So instead of jumping into showing how that kind of manipulation of spatial information is optics stuff, I'm going to illustrate some of the definitions of optics with some simpler examples, and I'm going to show them independently because they have some utility in their own right when they're specialized like this, and hopefully it should get across some nice ideas, even if you're not entirely on board with separation logic as an application. So the key idea you need for this when you're specializing, when you're looking at optics, or at least the degenerate form of optics, when you're specialized to preorders and prosets, is that monoids and their actions are a pretty good model of the notion of contexts and putting things into contexts and like filling holes in contexts. So none of this is a definition or anything yet. This is just listing some notation and trying to give an intuition for the purpose I'm going to be putting monoid actions to. If you have this monoid, think of the elements as contexts and think of the action as on something else as placing that thing into the context. So like, imagine that an element of M is a context, some kind of thing which has some holes in it. And imagine that when it acts on an element of X, you're filling the holes with that thing. And then you get out another element in that set by filling those holes. So the example, running example that I'm going to use, and I'm going to go back to that slide in a second if you didn't finish looking at it. I just want to show this example, is let's say that your elements of M are pairs of strings, which are a prefix and a suffix, so you can write them like this. And the operation is nesting. So if you have S with a hole in the middle and T, and U with a hole in the middle and V, then nesting U and V inside of S and then T gives you this. And the action on the set of strings is inserting the string into the middle, so that gives you this. So you can nest a bunch of these contexts for strings inside of each other, and then you can fill the hole with another string. Oh. So then, if you keep that idea in mind, if you keep that example in mind, then you can look at this notation, and the idea is that more generally, you can kind of try to see any monoid action as being sort of similar to that. Think of the elements of the monoid as being like that, context with a hole in them that you can place elements of the set. Look at the identity of the monoid as a whole. So when you place something into it, you just get that thing. Think of the operation of the monoid as nesting something context inside another context. So you fill the holes in the outer context with the inner context, but you leave the holes in the inner context alone. So those are still there. And then the monoid has the left regular action on itself, which is just multiplication. So that sort of makes what I just described itself a case of filling in the hole with something. And the monoid laws look like this, and I'm kind of rambling. I should probably just move forward. Hopefully that's clear.
Yeah, I think it's clear.
Okay. So fix a preordered monoid in a preordered left M sets X and Y. So I'm leaving this kind of implicit, but everything here needs to be monotone. So the multiplication for the monoid needs to be monotone as a function from M cross M to M, and the actions need to be monotone as functions from M cross X to X and M cross Y to Y. So then this is not actually the definition in the paper I'm citing, and the full citation appears later. This is the paper Profunctor Optics, a categorical update, but this is a case of this definition if you specialize it. So you can define this proset optic XY. So the underlying set is just the product of these M sets, but we're going to write elements like this. And the idea here is to think of this as being a formal expression that means like the act of changing from A to B, or the relationship from A to B, or something like that. I'll pronounce it as something like the change from A to B, or something like that. That's not a standard notation. I've invented it for this talk. So I'll write this squiggly arrow for the ordering rather than a less than or equal to, and it's defined by this. So and then you can read it as something like induces or gives rise to or extends to. So read this as the change from A to B extends to the change from S to T if there's some context such that S is less than or equal to A in that context. And then you can replace A with B, and then that's less than or equal to T. So the idea is sort of that like you're increasing from S to something, and then you're taking another step by swapping out A for B while leaving this context alone, and then you're taking another step to go to T. And so this overall process, as you can see, is sort of changing from S to T, but it's induced in a certain sense by changing from A to B because that's sort of the gap here. It's the only part which isn't itself just an increase in a preorder. And the key part here is that you need there to be some context which it occurs within. So this is probably going to look a lot clearer if I point out this example, or hopefully you've already looked at it. But if you use that monoid that I showed, and you use the discrete preorder on all the objects, then you have these. The change from M to mad induces the change from me to made, and that induces the change from edit me to edit made. Because in each of these cases, you have this context. Here, the context is just a prefix, an empty prefix, and a suffix of E. And in this case, the context is a prefix of edit space and a suffix of exclamation point. So what's happening is that you're saying that this is equal to this in that context, and then you can change to this in that context, and that's this. I'm going to move forward. I'm low on time. So let's say that a relation between X and, oh, sorry, one thing I maybe should have pointed out last time. These are two different actions. It's probably worth pointing out because A and B are elements of different sets. This is in X, this is in Y. So it's a little weird to talk about changing from one to the other, but it is useful in general. So this is slightly misleading notation, but so a relation between X and Y is order respecting if it satisfies this, and it's context respecting if it satisfies this. And being order respecting is equivalent to being antitone in the first argument and monotone in the second argument as a function to truth values. And being context respecting is, well, it's this. If a relation holds between two things, it also holds when you extend both of them by any context. So an example is an anagram of for strings. So like if A is an anagram of B, then if you prefix and suffix both of them, it's still an anagram because, I mean, think it through. But anyway, the pre-order case of a theorem in section 4.4 is going to look like these are equivalent. The change from A to B induces the change from S to T, and for every order respecting and context respecting relation, ARB implies SRT. So you can kind of see this as meaning that like you can instantiate or replace this triangle with an R whenever it's order respecting and context respecting. Or you can think of the triangle as being a sort of like a formal universal context respecting relation, and the squiggly arrow as being like a formal implication between those. And then this is like the universal property in question. And for how you can actually use this, since is an anagram of satisfies these properties, it satisfies this property trivially because since the order is equality in both of these cases, this is trivial. We have this. The change from act to cat induces the change from hello act to hello cat. So if we know that act is an anagram of cat, we can conclude that hello act is an anagram of hello cat by this. This to this, you basically just do by, filling this in. I mean, it's a pretty straightforward elementary argument. This to this, you can do by defining a relation in terms of this, showing its context respecting and order respecting. And it's basically kind of a Yoneda style argument. And this is all a case of profunctor optics. We've just been working omega enriched, where omega is the set of truth values. So when you're enriched over omega, instead of having Hom sets, you have Hom truth values. So a category just becomes a proset because you don't have a whole set of morphisms from A to B. You just have whether or not A is less than or equal to B. Monodal categories become just preordered monoids. Actigories become preordered sets with actions of a monoid. Cohens become just existential quantifiers. Profunctors become order respecting relations. And Tambara modules become order respecting relations that are context respecting. So, these two really are just instances, these two together really are the definition of a Tambara module when you're working omega enriched. And an inequality in this proset that I've defined above is the same thing as a Hom set in the optic category, which you can see defined in, say, this paper. And one thing that's worth noting is that usually when people use the noun optic as a noun, what they mean is they mean an element of a Hom set in one of these categories that you make using this construction. But since now we have posets instead of categories, we don't really have optics per se. So the closest analogy to an optic would be like a proof of an instance of the Scugliero relation. So even though I keep saying that I'm applying optics or whatever, I don't actually have any optics per se as things. So that's a little awkward, but anyway. So I'm just gonna take a moment to plug some terminology that I've coined that I like, which is that since omega is less rich than the category of sets, you're not really enriching, you're depleting. So I like to call working omega enriched as working depleted. So anyway. I only have 10 minutes left, but hopefully I can talk a little bit about how this all ties together. So let S be the proset of assertions with the ordering of entailment. If you define a relation which relates assertions when they are a valid pair of a precondition and postcondition as in a Hoare triple for a given command, then that relation is order respecting. That's the rule of consequence. So that's a depleted profunctor. That's a order respecting relation equivalently. That's exactly what the rule of consequence states. Similarly, let the monoid of contexts be S itself under the operation of separating conjunction. In an affine separation logic, your unit's going to be true. In a linear separation logic, you'll have an assertion which says that you have no resources, and that's going to be a unit. But whatever. The point is it's a monoid. So this also forms a preordered left S set under the left regular action on itself. So what that means is that contexts are just assertions, and to place an assertion into a larger context, you just take the separating conjunction. And that sort of matches with the idea that in the frame rule, the F is a larger context that you're working in, sort of. Like you're talking about the program, the larger context that your program fragment is working in, and that context is just the assertion that you're making, the assertion that you're making about the rest of the program state. So if you replace these Hoare triples with the notation that I introduced above, and you replace these separating conjunctions with the brace notation that I've been using, this is exactly the same thing as saying that it's context respecting. So this is, and I just established that it was order respecting. So this is a depleted temporal module, which is, so literally the content of the rule of consequence and the rule and the frame rule are that the Hoare triple relation is a depleted temporal module. If you want to use fancy terminology. Sorry, what was I gonna say? So then, using the key fact that inequality in an optic proset lets you take such relations and extend them, you get this rule, which says that if you have this thing which says that the change from P to Q, assertion P to P, assertion Q, induces a change from assertion R to assertion R prime, then this Hoare triple implies this Hoare triple. And that looks a lot like ramification. And there's just one final step to get there, which is, okay, I only have 5 minutes left, so I'm going to kind of fast forward a little bit. But basically, if you have a certain adjunction, which is established in Mitchell-Riley's paper, Categories of Optics, then you have this concrete representation formula, which says that you can correspond Hom sets in your optic category to Hom sets in one of your original categories. Or here, you can correspond inequalities in your optic proset to inequalities in one of your original prosets. And that's exactly the entailment in the Ramified rule. So if you replace the optic proset inequality in the previous slide with the concrete representation given by that theorem, you get the Ramified rule. And strictly speaking, the version in the paper that I cited has some stuff about side conditions on occurrences of variables, but that's kind of a whole, it's a lot to get into. I have some other technology for working with that, but I'm not going to talk about it. So what? I've derived the Ramified rule using a bunch of fancy categorical terminology. So sure, the Ramified rule drops out of use arrow, the optic proset inequality to focus proof when the statement is A or B for a depleted temporal module R and doing injunction, blah, blah, blah. But if you use these two theorems, which are known in the literature on optics, you just need to plug in the right M, X, Y, and R, and putting those two together immediately gives you the Ramified rule. Temporal modules and injunctions and actions, etc., have tons of categorical structure, which is really useful for building all kinds of other M's, X, Y's, and R's. Like temporal modules from the morphisms of a category, whose objects are preordered left M sets. And this is actually probably like a pro-arrow equipment or something for a category whose morphisms are lax equivariant monotone functions or something like that. This is all a decategorification of like a equivariant version of the category of profunctors. There's a ton of stuff you can say. Altogether, depleted optics and temporal modules give you this unified framework for like relating a couple like stuff that you can see in a number of different places in the literature on separation logic to each other and manufacturing more of it and the existing stuff by exploiting all kinds of different category theoretic structure that is very well established and lets you give very concise proofs. Like, seriously, you would not believe how much mileage I've gotten out of the adjoint triple of quantifiers. Like, I mentioned earlier that there's this magic wand as frame paper, which involves representing partial data structures using a wand thing and a for all. And for example, if you want to get something that involves these quantifiers nested somewhere inside that wand, then you can compose some quantifiers with your action, with your monoidal action or something like, with your monoid action or something like that. And then if you want a concrete representation for that, you need an adjunction, and then you can apply this and all kinds of stuff works. So there's a couple of future directions that I have in mind for this. One useful monoid of context for acting on stuff is the endomorphism monoid for objects in this category of quantal valued matrices, which you can read about on the NM page quantaloid. But it would be a lot more useful if I could have the whole category acting on stuff. But the definition of the optic category, or in this case, the optic proset, only uses a monoid action or a monoidal category action, as opposed to a category action or a monoid or a bicategory action. So a generalized definition of optics that allows something more than a monoidal category or monoid to act would allow a very useful action here, which would allow more polymorphic versions of what I've already defined. And I think it would be interesting to try and look into whether you could use this stuff to develop like more ergonomic interfaces for proof assistants, or not for proof assistants themselves, but for libraries for separation logic and proof assistants, because I have been working with the verified software toolchain, and I've made a couple of little worked examples of some of this stuff because I've formalized most of the stuff that I've covered in the talk in Coq, but I haven't done a ton of actual program verification using it. And I'm interested to see like how useful it can be in practice. And also I'm wonder what other applications there might be for specializing optics to posets. Like separation logic is probably not the only place they crop up. And that's 2 p.m. Wow.
Great. Good. So if anyone has questions, they could either, so let's thank the speaker. First of all, we can all virtually clap. I will actually clap. Oh, I hear some, okay, that was very loud there. That's great. Different amounts of echo on your claps. So let's, if anyone has any, you could ask them out loud here if you like, as long as you don't ask them all at once. Does anyone have any questions that they want to do that way? Or it's possible that people want to shift right over to...
I'll ask a quick question.
Okie doke. Hi, Mike.
If you could go back a few slides. So the relation that you got from Hoare logic, yeah, here, this HC. So if I understood correctly, you were saying that for each command C, you get an HC. Mm-hmm. But then you were saying that this HC is sort of a depleted version of a profunctor. So would it be natural to consider the collection of all commands as inducing a non-depleted profunctor?
I'm not sure whether they would induce a non-depleted profunctor, but commands, I worked this out a while back, that commands, if you consider them as forming a monoid with sort of an empty command like skip as the unit, you might need to quotient or something in order to do that, then you can do like a displayed category type thing where you have a functor from that into like omega prof or something, and then so you send C to HC, and then that displays a proset over this monoid, and you can kind of characterize certain, I think you can actually kind of characterize certain bits of Hoare logic that way, like the fact that it's lax is the, I believe, if I recall correctly, the rule of sequencing that I showed up here.
Thanks.
So Matteo had a question, which you should probably ask out loud, which requires turning on your mic, Matteo. So Matteo said.
Okay, sorry.
Okay. Yep.
It was in a noisy environment. So the triple adjoint string is really interesting because it's the meat of much of Fantario semantics. So did you investigate this triple in the context of omega sets? Hence,
Of what, sorry?
In the context of yeah, omega omega enriched category theory or depleted category theory, as you call it.
I'm sorry, what was the question?
Is that a junction the same we have in usual setting? The junction existence, delta, and for all.
Oh, the one that I had in mind, the one that I was talking about here was, I was thinking of the one where actually to be a little more precise, I believe I meant the adjunction between colimit, diagonal, and limit, with a discrete category as the, or so more concretely, that would be
Alright.
soup, diagonal, and inf.
Yeah.
But I write it as exists in for all because that's what I'm using. That's what inf and soup mean in this context, because we're talking about assertions and we're interpreting quantifiers. Does that answer the question, or?
Yeah.
Okay.
We can talk maybe later on Zulip about what we can get out of this.
Okay.
Thank you.
Okay, well, why don't we repair to Zulip and keep talking about these things. This is a really interesting talk. I actually understood Hoare logic, or at least I'm under the delusion of understanding, which is just as good when you're attending a talk. And I even understood how it's connected to optics, which is remarkable because I don't understand optics. So it was very, very good at covering a bunch of different topics and wrapping them up into a nice package.
Cool.
I have one question before we go, which is just how, I don't know much about how much do people really use Hoare logic for reasoning about imperative programming? Do they use it for proving correctness of programs a lot or a little?
If they are formally proving things about programs, it's like ubiquitous. Like it's sort of a very standard way of approaching it. But I mean, if you're talking about like just people doing programming as their day job, then probably it's not something that you could necessarily expect a random person working as a programmer to know about.
Well, I'm a programmer, and I certainly used it when I program, even if I didn't write it down explicitly. It was the way I was thinking a lot.
Well, I mean, I'm not saying that most programmers don't. I'm just saying that you wouldn't necessarily expect all of them to. It's not like ubiquitous.
I think you're right that most don't.
Okay.
Well, but anyway, that's still very promising for me then if it's a widely used tool for programming verification and it fits into this framework. Because I don't do much computer stuff, but I often hear people talk about how category theory is mainly good for functional programming, not imperative programming. So it's be very nice to advocate its applicability to Hoare logic and therefore imperative programming. It sounds like that's what your program is.
I have one question, if I may. So this whole thing is based on the fact that separation logic is in a monoidal closed category. So there's this monoidal structure, the star, the separation product. I wonder, is there any other monoidal structure in separation logic sort of corresponding to a sum rather than a product? Then we could use it to define things like not only lenses but also prisms.
That's open-ended enough that it might be better to talk about it on the Zulip.
It's not already sitting there in the literature.
It's not. Well, it's not. I mean,
visible.
I don't know personally of any literature on optics and posets already. So unless somebody else does, I don't have an answer.
I also have a small question. So you mentioned doing something in Coq. The way I can kind of imagine it is basically that you would use Hoare triple to understand how to transform contexts of your proof state in tactics. Is that what you have in mind, or?
Use a Hoare triple. Do you mean use an optic statement? An optic inequality?
Yeah, I mean, basically, when you say you have these pre and post conditions, for example, then I don't see right now how you would really have this in a setting of type functional programming. But if you want to use this to work with modification of proof state, that's the only way I see it right now. Is that what you're thinking of, or?
No, I meant like if you're proving, like there are frameworks for working in Coq with separation logic. Like separation logic is embedded within Coq. Like for example, there's Iris and there's the verified software toolchain, for example, and they do an embedding of separation logic as a semantic model in Coq, and then you can make statements of separation logic and prove them by applying like the lemmas that say like certain properties hold a separating conjunction, as opposed to reasoning directly in the logic as a syntactic system.
Okay.
Does that like relate to what you're asking? I'm not sure I 100% followed what you were saying.
I'm not sure. I'm just when I saw this Hoare logic, it really looked like well, more like traditional programming with modifications of state to me. And so when you mentioned Coq, this is what I was thinking of. Yeah, it was just the question of if this is what you had in mind, but seems like you were thinking of something different.
I mean,
so I think of it like, for example, if you compose two Hoare triples, then you would have like a composition of tactics or something. That's kind of what I was thinking of.
It sounds to me like you're thinking of something at a at like a shallower level of embedding than what I'm talking about.
Yeah.
I don't know. It sounds like you're talking about something a little more open-ended than
Yeah.
than what questions right now should be.
Why don't we repair over to Zulip and let chaos reign as usual over there. Productive chaos, usually. Okay, so thanks, Sarah, again for the talk. And I'm going to grab a cup of coffee and then come back.